Hey everyone, I'm Dr. Surjit Singh. In this video on Python via examples, we shall talk about summation of infinite series. Let us begin. In this session, we will learn about summation of infinite series. We'll discuss Taylor series for some common functions. We'll discuss the examples of e to power x and sin x. We'll learn about relation between terms to enhance the speed of evaluation of the series. We'll discuss about the rate of convergence of the series and about the diverging series. Many of the mathematical functions are defined as sum of infinite series, which are known as Taylor series. For example, the Taylor series for e to power x is defined as the sum of an infinite series 1 plus x squared by 2 factorial plus x cubed by 3 factorial and so on. Sum of infinite series is possible if it converges to a finite value, which means that the effect of n terms to the summation is insignificant. It means that the limiting value of the ratio of the consecutive two terms near the end of the series tends to become 0. Let us import factorial function from math library. We now proceed to find the value of e by selecting x equal to 1. We store 0 in result and then start a loop for adding the terms of the series one by one to the result. Present loop will add first 5 terms of the series. When I is 0, the term is x to power 0 divided by factorial of 0, which is 1. We add it to result and print the values of I term and result. Next 4 terms are 1, 1 by 2, 1 by 6 and 1 by 24. We add these terms to result and come out of the loop. Let us compare the final value of result with the actual value of E. In 5 iterations, our result is correct up to 1 decimal place. Just 4 more terms give the result which is correct up to 5 decimal places. It means that convergence of the series is very fast. We also notice that the final term is nearly 0. Even if we add up to 100 terms, the result remains the same. It means that the sum has converged and the subsequent terms have no effect up to 5 decimal places. But do we have to find factorial of every term? The answer is no. It is a wastage of time. To learn about this, let us rewrite the program. Just for a change, this time we take a new value of x. This value is commonly used in science. It is the log of 10 to the base e. So, for this value of x, the sum of series should be 10. In this form of the program, we will not need the factorial function. We take first term outside of the loop and make it also the starting value of result. Therefore, we initiate the loop this time with I equal to 1 as the starting value. Inside the loop, we make use of the old value of the term. We notice that the ratio of the new and old terms is always x by I. We will use this relation to find subsequent terms. Old term is 1, therefore for I equal to 1, the new value of the term becomes x. This way, we do away with the factorial function, which saves a lot of time. We add this term also to result and print it. In the next iteration, with I equal to 2, we again multiply the old term, that is x, with x by 2. The new term becomes x squared by 2. We print it and add this also to result. After repeating the process for 13 terms, final value of result becomes 10. This output shows that for the present value of x also, the term decreases very fast. Convergence is achieved to the 4 decimal places in just 13 terms. The last term is 0 up to 4 decimal places. The result remains 10 even if we proceed for 1000 terms. We can decide about the suitable criteria of convergence and incorporate in the program to terminate the loop. Sinx is another function for which also Taylor series is known. In this series, the term change their sign alternatively. If angle is in degrees, we convert it into radians. In this case also, we save the first term in result and then start the loop with initial I equal to 3. In this series, ratio between consecutive terms is minus x squared by I into I minus 1. So the old term, which is x, now becomes minus x cubed by 6. We add the term to result and print it. We increase I by 2 in each iteration. In this series, convergence is faster than even the previous example because we have a square term in the denominator. In a single iteration of the loop, result is correct up to 3 decimal places. Subsequent terms make minimal contributions to the result, which is 0.5. That is the value of sine of 30 degrees. For pi, we have the Leibniz series for pi by 4. We take first term into result, its sign is positive. We start a loop to add 5 more terms to the result. I starts with 3. Sign of 3 is minus 1. We change sign in every iteration and it will alternate between plus and minus. We now add minus 1 by 3 to result and print the sign of the term and the value of pi that we have got so far. In the next iteration, we increase I by 2. It becomes 5. Sign changes from minus 1 to become plus 1. We add plus 1 by 5 to the result and print the sign and the value of pi. 3 more iterations give pi value close to 3, but the error is still significant. This means that convergence of the series of pi is very slow. So we now proceed to add 100 terms of the series. Still, the result is correct only up to one place of decimal. Next, we now proceed to add 1000 terms to the series. The result is now correct to 2 decimal places. Results are oscillating around pi, so let us find the average of the last two values, which is given here. Its error is beyond the fifth place of decimal. As the convergence of this series is very slow, so for the same accuracy, we need a large number of terms than the previous examples. End of convergence is decided by comparing the last few values of the sum of series. It is well known in mathematics that determination of pi is far more time consuming than determination of E. Latest challenge taken in pi is in finding its digit at the 100 trillionth place of the decimal, and this digit has been found to be 0. This computation took 157 days of continuous processing on a very fast computer. Of course, such values of pi remain in the computer memory because we cannot print such a long number on any output device, nor do we need pi to this accuracy. No pattern has been found in the decimal digits, so pi is certainly an irrational number. Lastly, consider the series shown here. It is a simple series in which terms are decreasing continuously. Term at infinity is 0. But still, this series does not converge to a definite value. Program is fairly simple. Sum of the first 5 terms is shown here. for testing the program. The result is increasing and it continues to increase. Even after 100 million terms, the result does not converge to a final value. So we must first ensure convergence of the series before summing it up. For diverging series, no criterion will terminate the loop and the process becomes endless. Low value of a term is not enough to conclude that we have achieved convergence. Collective effect of subsequent terms can be significant. Notice that we have introduced showVal as a variable to print results for some selected values only. In this session, we introduced Taylor series for common functions. We discussed the examples of e to power x and sin x. Convergence is very fast for these two functions. We also learned that whenever possible, we must find the ratio between terms to find them quickly. We then took the series to find the value of pi. We discussed about the rate of convergence of the series and the criteria to terminate the summation of the series. Lastly, we also discussed about the diverging series. I hope you enjoyed the video. Please feel free to ask for further clarifications on my email address given below. I'm looking forward to your comments. Please stay tuned for more such videos.